Thank you, Jessica. I'm conscious that everyone's minds will be moving towards what's on the buffet rather than Midas modelling, so we'll try and crack through this fairly quickly. So just a brief introduction. There's some facts there on the right that you may or may not know about Mott MacDonald. Hock and myself have between us nearly 30 years experience in the design, planning and construction of primarily heavy civils underground projects, so mainly shafts and deep station boxes. So Mott MacDonald, we're using GTS NX for these three main reasons. Primarily that we can get away from two separate independent models for a geotechnical and a structural analysis, so we can move away from this spring approach for structural design and have a soil continuum around our underground structure. The 4D, what I call 4D numerical modelling, is key. So a lot of the problems we face now in the real world are heavily three-dimensional and also have a time aspect to them. And at Mott's now, we're going what we're calling going digital by default. And as BIM becomes more and more prevalent in project delivery, we need an analysis tool that is compatible with all these digital data sets that we have nowadays. So at the bottom, there's an example just where we've imported non-planar ground stratigraphy from a software called Leapfrog, which models is a tool we use for modelling complex geological sequences. Import that into Midas GTS NX, chop up our solid geometry, and then from there go ahead with meshing to have our structure within it. Another example of that is, this was a concrete-faced rockfill dam in Colombia, where we were given the topography as a DXF by the client. We were able to import that into Midas using Terrain Geometry Maker, overlay that with a DXF wireframe of the dam, and then create our solid geometry. So we've been using Midas since 2015, just a list of some of the typical applications we've used it for. So the rest of the presentation we'll talk about three specific projects. I'll cover two, and then Hock will cover a third, where we face specific challenges and how we utilised GTS NX to overcome those. So the first project application is a 10-metre cut and cover excavation in Qatar for a new railway, where we were the independent checker. So the main cut and cover box, you can see at the top of the diagram, is 900 diameter secant pile excavation. But fairly late on in the design process, this zone 3A down the bottom became required and was tacked on to our check at the late stage. So we were required to check both the wall and the temporary works for this excavation next to the main excavation. Now the form of the wall for this zone 3A was formed by micropiles, so augering a 300 diameter hole and then grouting in a steel section in this staggered arrangement. So the challenge we faced here was that how do we actually model this quickly and efficiently, bearing in mind that we're doing an independent check, and as always with these things, pressure is on time and budget, so we need an efficient way of getting some forces out for this wall quickly. So normally, if we're faced with a pile wall, we'll try and approximate reality in a numerical model by a shell element, and the shell would provide the equivalent stiffness, both axial and bending, and unit weight as our pile wall. Adopting this approach, you could come up with the parameters you can see on the bottom of the slide there for each micropile row, but that doesn't quite solve our problem of modelling it as a single shell. So we set up a 2D model that included both these rows, as you can see on the left, and lunchtime. I read my mind. So we set up a 2D model just with those two equivalent shells for each pile row, and then alongside that created a 3D model that was long enough to approximate the plane strain condition that we get in the 2D model, and then played around with the thickness of that single shell and its other parameters, primarily the stiffness, to match the behaviour that we saw in the 2D. So that we come up with a single shell that actually mimics the movements that we think we'd get from the 2D model. Thank you. Welcome back, everyone. So, just a quick recap. We're trying to model 2 rows of micropiles in a staggered formation in a 3-dimensional numerical model. So, as I was describing before we were interrupted, we set up a 2D model with both rows of piles modelled as a beam here or an equivalent shell, and then a similar 3D model to approximate plane strain conditions with just a single shell element, and came up with this final thickness for our shell of about 0.155 meters, with the stiffness and weight double that of a single row. So this is just a couple of shots of the 3D model that we ended up with in GTS NX, and on the right hand side are the primary outputs that we were looking at, on the bottom right being the bending in the wall or the micropiles, and on the top right the forces to be taken by the temporary propping. So once we've got our results from our equivalent shell, the next question is, well, where's the load going to go between these 2 rows of micropiles? And again, we used the 2D model to look at how the forces are shared between the 2 walls. So this is the graph on the bottom left. The bending moment results from the 2D model. For the front wall is the solid lines, and the back wall is the dashed lines at various stages of the construction sequence. So for example, down here where we've got hogging region at the passive support of the rock beneath the formation level, the share of bending is about 60% going to the front wall and 40% going to the back wall, which sounds sensible enough. If you look at the shear force results, almost all the load in terms of shear is taken by the first row of micropiles. Again, which is what you'd expect, because that's the piece of the wall that's seeing the propping forces first. So this is how we broke the results we got from our 3D model back down into individual forces for the design. Okay, so second project application is for a ventilation shaft in central London. This is a live, ongoing project, so all these images are very much hot off the press. It's a 20-metre cubed excavation within a 200 mil diameter contig pile wall. These shots are just from the BIM model, the one on the left being the whole substructure and then a 4-storey head house, and on the right just being the internal substructure. We've already seen London stratigraphy today, so we don't need to go over that. The only point of interest for this project is this potential sand channel somewhere near to the formation level that may or may not be water bearing. So that's something we're going to have to consider in our design and analysis. So the challenge here is that we've got a relatively complicated structure with many different elements, and we want to create one single model to make the design as efficient as possible, so we're not having to go back and forth between geotechnical models and structural models and the inevitable miscommunications that can occur with these. So again, this is just breaking them down into the various elements. So So we've created this 3D model. The view on the right is just our structure from Midas. And we've done this, again, in this common data environment. We've utilised the existing BIM model to create a wireframe CAD geometry of our structure, and imported that to GTS NX and imprinted it on our solid geometry, so that when we mesh up our soil, we've got nodal connectivity at all the points where our slabs and our walls and any columns will be touching the ground. So again, that's just some visualizations of the different elements within the model. Just taking a, you can see on this one actually. The key sort of structural modelling aspect to this is that we're modelling the capping beam and the base slab and a couple of very chunky wailers that are hidden in around the back of this vent opening. We're modelling those as solid volume elements in the model with gauging elements within them to extract structural forces, because the stiffness that's provided by these sort of elements is very, very significant. So we don't want to underestimate the stiffness of the structure. And here's just some views of the capping beam with a gauging beam within it and the resulting bending moments. This also increases the design efficiency of our structures, because we're smoothing out those peaky bending moments that you get if you use just a stick to model a beam. Similarly on the right hand side for the large wailing beams around the openings of the slab. So I think this is my last slide, and it's just to highlight the benefits that Midas gives in terms of these 4D effects. So here in the middle we've got our main shaft structure. We've got a SCL tunnel that will be connected in. And on the corner here is going to be a not much smaller than the main vent shaft, but not inconsequential temporary shaft excavation to put in a sewer, pipe jack in a sewer. So this is about 12 metres square, 7 metres deep, next to our 20 metre cube, and very close on the corner here, maybe 2 or 3 metres. And to look at this in 2D, if we modelled this in as a section 2D through here, this would have a large impact on this. Because of where it's situated on the corner, the 3D effects mean that in reality it may have very, very little impact given the stiffness of the capping beam around the top of the box. So with Midas we're able to, one, model these 3D effects, but two, we can, because currently there's uncertainty as to when this will go in, using the construction sequence modelling in Midas, we can drop this in at any point in our sequence. So if in 6 months' time the client says, actually, this is going in whilst we're doing the box, we can very efficiently start to look at the impacts that might have. So I think that's all from me. So I'll hand over to Hock, who will now talk about our third project, which is the Crossrail shaft on Moorgate.
Hello everyone, I'm Hock. The third example they want to talk about is Crossrail Moorgate shaft. It's the same structure that Adin Prof mentioned earlier this morning. So the Crossrail shaft is the deepest shaft on Crossrail project. It's about 42 meter deep. In plan, it's roughly 35 meter by 35 meter, formed by 1.2 meter thick D walls, extended down to 55 meter deep. As you can see in this image below, the site is highly constrained, especially the 100 years old Northern Line tunnel, which showed by these dark grey tunnels. This is the shaft. It's just about 4 meters away from the shaft wall. The ground condition is a typical London sequence. I don't need to mention, but just to point out a few points, most people know about Upper London Quay. but the lower London clay is less well understood, but the lumber group even worse because it's very complex. It's intrinsically very highly variable. So it creates more uncertainty in terms of ground modeling. So the shaft was constructed top-down through the application of an observation method, what we call it verification process. The reason we introduced this process was because we need to speed up the shaft constructions. This is because the start of the D-wall constructions was delayed by 11 months before we doing anything due to the difficulties to remove the existing piles within the footprint of the shaft. So by applying this process, we managed to omit all the temporary steel props near the bottom of the shaft and also half the construction stages for the final 4 levels of rim beams. So this not only we enable the shaft to be completed earlier, where the construction program was shortened by 14 weeks and the potential 11 months was delayed. There are further details about this already published in these 2 papers. If you want a copy of them, just let me know. So I'm not going to discuss further here. So when the shaft was completed in late 2014, the maximum wall displacement here for the east wall is recorded by 25 mil. So later we found that the east wall movement was gradually increased. So by early 2016, the east wall was recorded about 40 mil. So we found that this was due to the grouting works behind the east wall. The grouting works is mainly to facilitate the AP9 SCL tunnel constructions. As you can see here, there are SCL works going on here, and this is the AP9. And this is Northern Line, about 4 meters away. This is the east wall. So as you can see the figure on the right, you can see the east wall movement approaching near 40. So this was great concern at that time because the red trigger limit is going to be breached. So once the red trigger breach means that all the grouting work need to be stopped, and there will be cause a significant delay to the SCL tunneling works. So we were asked by Crossrail at that time to carry out further assessment on the shaft to decide whether we can further relax the red trigger limits. So we decided to use Midas GTS NX. So we created an integrated 3D model, making use of beam. The D-wall panels were modeled using volume elements based on the as-built D-wall layout. One of the challenges is we want to prevent any transfer of tensile stresses in between the D-wall panels. So what we did is we introduced additional volume elements inside there, try to manage the tensile stresses within those elements. And all other internal structures like rim beams, columns, lining wall, they all imported from the existing 3D models. And this has reduced the modeling time significantly. As you can see in the next slide, the geometry is very, very complex. If you want to draw it using Midas GTS, it will be very, very time consuming. But for us to do this is very fast because we have already an existing 3D model. And so the whole model consists of more than 200,000 elements, making use of different type of elements within the Midas GTS NX. Prior to this assessment, the shaft was designed using a ground model we call A-star model, which developed by Mott. Basically, this A-star model is a non-linear stiffness conceptual framework, making use of different sources of data. For example, you can see the figures on these 2. They are the non-linear curves that we use for the London clay and the lumber group, making use of the advanced laboratory test data and also self-boiling pressure meter tests. So by doing this, we think that we have a more reliable non-linear stiffness curve to predict the ground movement. And this is what we show here, the A-star prediction versus site measurements. The submission I think is in dotted lines, yeah. And then the SR prediction, one is based on the GHH, the other one is based on GBH. But you can see if you base on the simple linear elastic perfectly plastic model like Moore column using Plaxis, you not only over predicting the displacement, but the shape also completely wrong. When your shape is wrong, means that your forces are all wrong. So for this assessment, we didn't use A-star. The main reason because there was no A-star model in the GTS NX. So maybe Midas can consider that. So in order to ensure we have a right stiffness for the GTS model, what we did is we calibrate the ground stiffness with side measurement, so that we have the right starting point. So as you can see here, this green curve is a calibrated wall displacement profile. The dotted line are the side measurement. So once we are happy with the model, we apply further grouting pressures given by the grouting contractors, and then the corresponding additional wall movement was predicted. And then we check the shaft, we make sure SLS and US checks are all within the capacities, and also especially the convergence of the rim beams. We also make sure it's okay, it's acceptable, and any additional potential movement at the northern lines tunnels still manageable. Then we relax the electrical limits. So when we satisfy all the stakeholders, the London and ground everyone, then we increase the electrical limits by another 10 mil, from original 40 to 50. So there was a great relief at that time, because the SL tunneling work could be continued as planned and completed within this region. So just to summarize, there's an existing continuous trend that underground structures are going much deeper and closer to sensitive facilities and heavier in design. When I say heavier, it means that there are a lot of steel reinforcement in the structures. So naturally, there will be a greater use of finite elements and also volume elements, because of we want to make use of beam. And also to control any uncertainties, also the observation method also become more and more common. So in Mott, how do we manage this? Is we try to push for an integrated model, means no springs. And then because we believe this not only improve efficiencies in terms of design and also delivery, but also improve communications and also try to cross the gap between structural and geotechnical engineers. And also civil engineering industry is also moving towards beam level 2. For example, HS2, all our model we deliver using 3D model. There's no 2D drawings anymore. And also 4D modeling, like what briefly mentioned by James just now. So by working in this common digital environment that leads to analysis 2, we believe it will improve coordinations between different parties and also reduce errors. So in Mott, Midas is one of the tools that we found very useful. We attempt to achieve the above. Thank you for your kind attention.